I'm awaiting your go.
Stand by. We're ready.
Thank you, Dina. Good evening. Before I introduce our speaker for this evening, I would like to make two announcements. The first one is for the members who attend 5 out of 9 InReach presentations between March and June. You will receive a special certificate of participation from DAS in July. So we encourage you to attend at least 5 out of 9 such InReach presentations. So that's number one. Number two, we are forming an astrophotography special interest group. Our speaker tonight will also be talking about this, but this particular group will be meeting on April 14, 7 p.m. And we encourage you, if you are interested to join, to send an email to astrophotogroup@denverastro.org. And our presenter will have that address on his chart as well. So let me introduce our speaker this evening, Joe Pineda. Joe has been a recently retired electrical engineer, and he spent most of his career designing, programming, testing, modeling, and simulating digital radio communication systems for aerospace industry, including the NASA space shuttle, the shuttle loads, space loads, the Orion capsule, and the Project Dream Chaser spacecraft. Joe has been an amateur astronomer since he joined DAS in 2017. So Joe, please proceed with your presentation.
Okay, so my name is Joe Pineda, as Dr. Unsoy said. So this is going to be an overview of astrophotography. The intent is this is an introduction which the special interest group will perform deeper dives into some of the subjects. And so this is mainly going to be about deep sky tonight, but we hope to have spectroscopy, solar, and planetary as part of our interest group. So this first photo is my very first effort in Colorado in the field. I went with a U.S. Air Force Academy graduate, John Miller, who he taught me how to camp in Colorado. He was a very fine fellow, and this was his favorite place to go fly fishing. And it also turned out to be a very nice place to take pictures. So I had my little $300 Newtonian, and the point of this trip was to get ready for the 2017 eclipse. Hang on just a second. One second. It's not letting me advance. Oh, there it is. Okay. So background, we're lucky to live in the state of Colorado. It has a lot of natural beauty, and people like fly fishing, they like hunting, they like whitewater rafting. Astronomy is another thing that you can do in the great outdoors that makes it a fun place to live in. So we're going to introduce astrophotography, the members who wish to explore the night sky further than their eyes can take them and explore the Colorado experience at the same time. We're going to follow a why, what, where, when, and how approach. We're going to focus on AP, but many of the techniques we're going to talk about tonight are going to be applicable to visual observing. One of the things that people always ask whenever I take a telescope in the field for picture taking is how much does it cost? Invariably, that subject always comes up, so we'll talk about that tonight. The subject of astrophotography is enormous. The details, there's so many deep dives you can go into this. So I'm going to put a lot of links in the presentation that you can go in deeper. However, if you really want to get to know a lot of this material, join the DAS special interest group on this subject. What I'm going to show you is just a way to get going on this. It's not the only way. I am from a town called Lamarck, Texas. It's on the Texas Gulf Coast. It's about 10 miles from Galveston, 20 miles from Johnson Space Center. That's where I grew up. I'm a retired electrical engineer, as Dr. Onsoi said. My focus has been radio communications, antenna, digital signal processing, embedded systems. I did some flight ops at JSC, mainly for the payload operations. I did a lot of MATLAB modeling and simulation for Lockheed Martin. Most of my career was at Lockheed. I spent 20 years at JSC, 10 years in Pennsylvania at the King of Prussia plant, and 10 years in the Waterton Canyon plant working Orion from contract award to the EFT-1 flight that occurred. I think it was January 2015. I can't remember. So my job for that program was the communications architecture, the antennas, the transponders, the signal processors, error correcting codes, and things of that nature. I retired and I got a part-time gig with Sierra Nevada in Louisville. A buddy of mine from NASA works there. And so I helped them out with their comm system on Project Dreamstage. So you'll probably hear more about that in the future. And but basically, as far as this subject is concerned, astrophotography, I'm not trained in astronomy. And so what you're going to see is a summary of everything I've learned since the 2017 solar eclipse. So here's how I take a look at astrophotography. Why do astrophotography? So my humble opinion, our eyes are pretty good. And they're miracles of nature. They're just amazing things. But they're not really designed to explore the cosmos. They're really designed to keep us alive or perpetuate the species. Telescopes, if you think of a telescope as collecting light, light is just another type of signal like radio. So I see telescopes as an antenna. And our eyes connected to the biggest telescope in the world is like connecting a crystal radio set to the Arecibo antenna. You know, so you can do better. And that's just my prejudice. I know I'm probably making the visual observers upset, but I'm sorry. Well, I'm not that sorry. So cameras augment our ability to see deep into space because they can integrate what they see over a longer period of time. Our eyes are less than a second. Computers augment the approach to taking pictures because you can have algorithmic improvement of signal to noise over multiple images of the same subject. I'm going to show you a book called by Charles Bracken. You'll want to look at chapter 2 on signals to noise to see why this is. Camping, why camping? Camping allows you to find a good spot that's dark. You can always go to the DAS Dark Sky site. That's a wonderful place. But camping allows you to persist at a given location. So it improves your likelihood of success. So if you have a bad night one night, maybe the next night is good. So with a combination of all these things, you can probably see further and farther than you could with a visual approach to astronomy. And also because it's fun. At least I think it's fun. So the way I see the system is you have your antenna, which is the scope. If you're capturing just luminance data, it's basically you have an amplitude modulated demodulator, and you're taking light amplitude and you're converting into volts, and you're integrating over time, and you'll dump your result and reset your integrator every time the exposure time ends. You digitize that, and that is shipped into computer memory. So what I just described is one pixel in a camera. So one thing to consider is that the photons in the image sensor are converted to electrons and stored for each pixel. There's a limit to how much you can store in a pixel, and that's called the well capacity of the pixel. And you can see more about that in the Charles Bracken book in chapter 1. The complexity and cost. So this is a very complicated subject. I think it is. You really are doing a lot of sophisticated things to make all this happen. So what you want to do is if you decide this is not for you, you want to be able to back out of the thing without having spent a lot of money. So a plan is to invest in a pair of binoculars. I would recommend some 10 times magnification, 50 millimeter aperture binoculars and a lawn chair. And then learn a planetarium program. There's a bunch of them out there that are free. Stellarium's a good one. And pick out targets, learn how to find objects in the sky. Just sit out on your back porch, and then learn how to camp, learn how to be self-sufficient in the field. Start in your yard, the DAS Dark Sky site, and subjective sites to follow. So basically, I'm advocating Visual astronomy is as a beginning for this whole process. Watch others, see what they do. One of the great things about being in an astronomy society is that you can learn from your mates in the group. So it's a wonderful thing. Read the DAS classifieds for used equipment. That'll save you some money. Visit your local astronomy store. There's one. It's on Colfax, I think, near Wadsworth. That's the Mile High Astronomy Store. I think the owner is a member of DAS. Oh, and so some books you can read. You don't have to read a whole library of books. You can get started. Probably one of the best books you can buy. It's a paperback on Amazon called the Deep Sky Imaging Primer. And remember, we're focusing on deep sky tonight, so we're not going to be talking about planetary. And the Backyard Astronomer's Guide, Dickinson and Dyer is another one. And Deep Sky Wonders. This is a great book if you're looking for targets and you want to know, oh, it's April. What's up in April? What are the best things to look for? So this is a continuation of initial effort by Sky and Telescope. The current curator is Sue French, and you can also get her monthly editorials in Sky and Telescope magazine. So this is a good book for that kind of thing. And then recently, Dina and Mehmet went to the Kalamazoo Astronomical Society. They have a white paper or PDF file on Introduction to Astrophotography. It's pretty good. We have part 5. I tried to embed it in this presentation, but I couldn't get PowerPoint to do it. So we have it. The APC will have it for your perusal, assuming you join. And I'm sure Des will just give it to you. And then once you've gone through all of that, step 8, build your first astrophotography rig. And so there's various ways to get started. So don't worry, it doesn't have to be really expensive. Okay, so we talked about why, now we're going to talk about where. So this photograph was taken obviously during the solar eclipse. This was my very first effort. So I had spent $300 on a 5-inch, I think it was 5-inch. Yeah, I think it was. Newtonian at telescopes.com. I happen to have a Nikon camera. I bought a T-ring adapter and a coupling tube to connect it to the scope. And I was able to grab this picture of the eclipse with that. That friend behind me is very brave. This guy I grew up with in Lamarck. His name is Alan Jones. His girlfriend there is holding a welder's glass in front of his Nikon. He's very brave. I wouldn't have done that. Anyways, so on my scope, you can see there's a sun filter on front of it. So never look directly at the sun or indirectly via a mirror. So on the upper right there, you can see a picture. If you look on the left side, you may see a solar flare. It's not a very good image, but it's not bad for a first effort, I guess. So on the left side, just a little red area here. It's kind of interesting. Okay, so step 1 to astrophotography or any kind of astronomy is avoid light pollution. I'm going to show you an easy way to do this. There's some NOAA, NASA data online that has sort of a map of the Earth and shows you where the bright spots are and the places you want to avoid. There is a device called a site quality meter, or SQM, that you can actually buy for about $138 from a company called Unihedron that will give you readings that are consistent with the NASA data. What you're looking for when you plan a field session is, what is a dark sky site? This is what you're looking for. And so there's 2 links to help you understand what a dark sky site is. But the easy solution is the dark sky site must provide a resource where the night sky brightness is routinely equal to or darker than 21.5 mag per arc second squared. So what does that mean? So the idea is, it came from an ancient Greek astronomer. His name is Hipparchos, I think. I can't pronounce it right. Who assigned a magnitude of 1 for the brightest stars visible to the naked eye in his day, and magnitude 6 to the faintest stars visible to the naked eye in his day. So bright stars had lower numbers, dimmer stars had higher numbers, And so 21.5 means that you could see a magnet. I think it means you can see a very, very dim star, 21.5, in the type of light pollution you have. So you want a large number for a very low level of light pollution. That's the number one thing you need to remember. There's a link down there at the bottom to a PDF file white paper on what all this, a little bit more detail on what this means. On the next slide, I'll give you a link that you can use to find what the sky brightness is for anywhere in the world using the US data for light pollution. By the way, the DAS Deep Sky site, Dark Sky site is pretty good based on this information. And I also heard the Jackson Lake State Park is pretty good. And there are others. I mean, it's sort of it's not as bad as everyone says is in this part of the country. And then star parties are generally set up at sites that meet the criterion. I'll show you Okie-Tex on the next slide. So here's the state of Colorado. Obviously, you can pick out Denver. Here's Boulder, Fort Collins. Down here, Castle Rock, Colorado Springs, Pueblo. Here's Trinidad. Down here, the I-25 corridor, basically. And then as you go out west, you can still see some areas around where all the ski lifts are and everything that are crowded. And you can basically use this map to find areas that you want. What you're looking for are the areas that don't have any green or yellow or red. And over on the right is legends. So we talked about SQM, site quality meter, mag per arc second square. Well, here's what you're looking for. See this sort of bluish black and then black area? That's these areas right here. Now, if you look at, for example, Okie-Tex, which is it's a star party held in Kenton, Oklahoma, that a lot of you go to, that's down here. And it's in it's very good area down here. And I think the Rocky Mountain Star Stare, let's see, you drive to Pueblo, which is here, and then you head off this way somewhere. So it's probably off this way somewhere. It's pretty good too. Oops. Let me go back. I hit the wrong button. Okay, so if you want to buy one of these site quality meters for your own use, I've checked it against this map, and it gives consistent results. You can get one from Unihedron for the $138. It has one button on it. It's very simple to use. It's a wonderful device to have if you're checking out your backyard or someplace else. And so if you want more about the VIIRS satellite data, you can find it here and in this link. Okay, so now that you know where you don't want to be because of light pollution, you can find a good campsite in the darker regions. So here's three of them that I've looked at. My favorite is Campendium. It has links to Colorado State Parks, national parks, BLM, free camping, etc. If you subscribe to this and pay the annual $20 for the fee, they'll tell you if you get cell service. They'll tell you the conditions of the roads. Some of the roads and to get to these places are washboards. Some have potholes. Some are almost inaccessible to anything but a four-wheeler Jeep or something. So you want to know that before you plan to go out there. So Campendium is really good for that kind of thing. And they'll even give you reviews like, oh, there were a bunch of guys riding ATVs at all hours of the night and you don't want to go there, or the neighbors were rude or something like that. So this is a good one to use. It tells you just about everything you want to know. Logistics. So I have a Subaru Outback, 2020 Subaru Outback. It has a payload capacity for towing of 2,700 pounds. And it has a tongue weight that it will allow it to carry a tongue weight of 270 pounds, a tenth of the hauling weight. So if you're going up in the mountains, all the trailer manufacturers around Colorado here say that you need to have about 1,000 pounds of margin. So I picked a trailer that weighs about 1,760 pounds. It's made by a company called Scamp. And that was my design goal. That met my design goal. But the thing is, if you're going to carry water or a lot of things up there in the high country, you have to think about things just like if you're flying an airplane. You have to worry about weight and balance, things like that. So water weighs 8.34 pounds per gallon. maybe what you should do is not buy, if you're going up in the high country, don't buy water till you get to Silverthorne or someplace on the other side of the Eisenhower Tunnel. That'll save you from maybe burning up your motor. Another things you need to worry about is, do you need 110 volts? Do you need security? State parks are probably your best bet. Some of them even have Wi-Fi. Read the reviews on Campendium. Check out road access alerts. It may be nice here, but I have a buddy that says you shouldn't go up to Kremling until after May because there's snow and wet and muddy roads up there until then. The other thing is, if you're going to spend all the money and go through all the trouble of getting up there, do a test run, do a dry run at your house or a local park. Do a simulation of what you're going to do before you go up there. Go through all your procedures, make sure all your hardware is configured, make sure all your cameras are focused and everything's collimated. Do whatever you have to do to make sure that when you get there, it's as smooth as glass. It won't be, but you can at least try. Try to have multiple ways to do the same thing. For example, can your iPad substitute for your laptop? In some cases, it can. What about food? If you buy food in Kremling and it spoils or something wasn't right or you have an allergy or something, maybe get some Mountain House at Walmart. They're like MREs or freeze dried. They're not all that great, but they're not bad. They'll keep you alive, I guess. Let's see, power supplies. So I have a Jackery 500 watt hour lithium power supply and solar array in case my camper battery fails. I also have an extra solar array. Let's see. When you get to a state park, if you look at the Google satellite maps of state parks, you got trees everywhere. You got this and that and the other that you may not like because it obscures your view of the sky. So YouTube has videos of drive-throughs. Some guy actually just drives through a state park or a campsite, and you see the road conditions, you see where the trees are, and it gives you a better idea of boots on the ground. You can see what things actually look like when you get there, and that's critical to make sure you have a pleasant experience when you're looking around. All right. So I found a place that wasn't a state park, wasn't a really BLM or any kind of land. It was actually a reservoir. It's called the Williams Fork Reservoir, and it's let's see, if you go to Kremling, north of Silverthorne, it's east-southeast about 10 miles from Kremling, and it's in sort of a valley. So the reservoir is run by the Parks Department, and they have policemen that go out there and patrol it to make sure you don't do anything bad to the water. It's a great place for boating, kayaking, having fun, in water sports. I didn't see any water skiers, but it's a peaceful place. Not a lot of people know about it. So I took my Kodiak canvas tent. It's a 10-foot by 10-foot tent in the picture. I took my my cooler. I set up my 8-inch SCT, and it was a great time. My son met me out there, and we had a great time playing around with the telescope. On the right there is, I'm going to show you a small astrophotography rig. This is the Horsehead Nebula and the Flame Nebula, the Star Alnitak, done in narrowband. A lot of people have taken this picture, and they all seem to look the same. So there are many like it, but this was mine. Anyway, time of night. For the subjects I like to image, my scope, I usually run from astronomical dusk till dawn. So what you're going to want is a web service that tells you what astronomical dusk to dawn is. And I'll show you that in a minute. I want my subjects that I'm going to take pictures of to be as close to zenith straight up as possible for the entire night as much as I can get. When it crosses the celestial meridian, which is a north to south line across the sky. It's darker there, and the path through the atmosphere is the shortest. So that's really what you want to get the best images. And I'll show you what will happen later if you don't do that. I want my rig to be all set up aligned to celestial north. I'll explain why. And I have an auto sequence that I engage 30 minutes before astronomical dusk. so that by the time the imaging session starts, that's when you that's when people come over. They say, what are you doing? What is this? What is that? And folks are naturally curious, and so you have to be ready for that. So if you have campsites that are busy, you want your astrophoto session to be automated. So we'll talk about that too. So the implication from all this is you need to know what subjects are highest in the sky when they cross the meridian. Will they fit your astrophoto rig's field of view? What the atmosphere will be like, and the moon is an issue, and all that. And you can get all this from two sources: a planetarium program and a web service. So I did over the past 5 years, I've done a lot of looking at planetarium programs, and I picked two, and I'll tell you why. For Sky Safari, that by far is my favorite. But the problem with Sky Safari is it only runs on Macs and iOS devices. But it's, for what it is, it's perfect. It doesn't cost very much. It has a beautiful user interface. It tells you what you need to know to get your job done with the astrophoto session. You can filter out the kind of subjects you want to look at. It'll tell you what's optimum for tonight, all that sort of stuff, although most of them will. The other one is Stellarium. I use that because I have a mount. I use that because sometimes I use a program called Nina, which is an astrophoto. It's free. It's an astrophoto scripting program that will do lots of the work you need and make your life a lot easier. And it doesn't currently work with Sky Safari. It works with Stellarium. So Stellarium's another good one. It's absolutely free, doesn't cost anything, has a great user interface. You can explain it to just about anybody in a couple of hours, and they can be able to use it. In fact, if you were going to start out with your binoculars and your lawn chair in your backyard, this might not be a bad way to go. If you got an iPad or an iPhone or a Mac, I would start with Sky Safari. You'll be a lot happier. It's really a cool program. All of these, by the way, on the screen are great. The only one I had problem with was Starry Night, and it was just buggy. I would tell it my scope configuration, my aperture, all that stuff, and it would work for a while and then would forget the whole config. So Starry Night was bought. It was an independent company. It was bought by Sky Safari, and I think they're working through the bugs. Maybe it will be okay. The nice thing about it is it will work on Windows, whereas Sky Safari works on Macs and iOS. So maybe that'll get better. I don't know. K-Stars is kind of unique. It works on Raspberry Pis, Linux machines, that sort of thing. And SkyX Pro is another good one. That one is what's called an all-in-one program. It will do your planetarium, but will also manage your astrophotography. And they say on their website they have a Raspberry Pi version available. Raspberry Pis are little single board computers. I don't know if you guys are familiar. You can go to Micro Center, you can get one, and they're about $50-$60 last I looked. So it makes your life less expensive. However, I've had mixed results with Raspberry Pis. I'll talk about that later. So planetarium program, here's an example. So I'm getting ready for a star party. I'm going to go to Okie-Tex, and I want to pick out the targets. I want to look at Okie-Tex. I've got a week. Maybe I image for one target over 2 or 3 nights. I don't want to waste a lot of time. I want to have everything figured out. I want to have contingencies planned. If this part of the sky is bad, I want to be able to find another part of the sky, things like that. So here's a step-by-step for that. So in Sky Safari, I would enter the scope and site data. So on the upper left here, I don't know if you can see, it's a little blurry. I apologize for that. I would put in my scope aperture, my focal length. I would put in my camera pixel size, length by width. And it would generate this rectangle and superimpose this rectangle on the planetarium field of view. And you could look in this rectangle in object one, and you could see the object you're looking at, how big of how much area in your field of view would it consume. In this particular case, I'm using a really wide field scope. So most of the things near this is near the celestial pole. Yeah, because there's Polaris. Most of the things are just stars. you could probably see Bold's Nebula, maybe the California Nebula, things like that, really huge objects with this. And you can have a lot of fun with a scope like that. But anyway, you have a rectangular field of view because the image sensor is rectangular, and this helps you sort of see what you're going to get in your final image. And you can also use this for composition and framing, and you can rotate this rotation angle down here so you can match the rotation angle of your clock angle, if you like, of your camera when you're pointing at a section of the sky. And then item 2 here is the filter criteria. So this is what you want to look at. So I picked bright nebula, comets, planetary nebula, globular clusters, and galaxies. Those are the things I wanted to look at when I was at Okie-Tex. And then so I said, don't show me planets, don't show me moons or double stars or any of that stuff. So those are the things I wanted to image. And down here, I wanted, because I have a really wide field of view, I want to say, in order to have something that's interesting to look at, I want, in a wide field camera, I want 10 arc minutes to 60 arc minutes, that thereabouts. And I don't want it to look at anything below 45 degrees of altitude. I want it to be reasonably high in the sky. So this is how you filter. And then the specific time range was October 1st, 8 p.m. to 5:20 a.m. And then that would be my filter. And so Sky Safari spits out a viewing list, an observing list. And you could use this for a visual observing if you like. And it would show you what your best targets are. So for the filter criteria I put in, so here's M2, a globular cluster. And then with my camera and my scope, this is what I would see. Yeah, it's a little small, but I could probably zoom in post-process and get a usable image of something interesting. Here's some other targets I could look at. So this really makes it reasonable. It saves you a lot of footwork. The other thing I would do is I would look at Sue French's Deep Sky Wonders, and I would match those, what she says is the most beautiful thing, aesthetics of what to look at, and I would go there. And then finally, I want sort of a graphic that shows in the lower right here, a graphic that shows the elevation of the object over the course of the evening. So the blue areas are daylight. Here's the sun, this curve here, and this curve represents elevation, and the x-axis is time. So in this curve, I see the sun setting. And then this where it transitions to astronomical night, that's where I would start imaging. So from this graph, I would say right here, when I start imaging at astronomical night, I would be at about 40 degrees elevation. And Messier 2, which is the object up here, would be 50 degrees at peak. And then it would cross the meridian right about here. I forget what this bar here is. That may just be the center of the graph. And then somewhere around 3 in the morning, it would probably be too low in the sky to be usable. So I could estimate the total amount of imaging time from this graph. And so here's the moon over here. And so the moon starts to rise at about 3 in the morning. So it's a good time to stop imaging when the moon starts to rise. So this gives you a lot of information. So the sun, the target, and the moon. Black is good. That's where you image. Y-axis is elevation. So that's good stuff to have. It's a very simple graph, and I use it all the time. The other thing we talked about is where the moon is, what the weather's like. There are many sources of information for that. I use Telescopius, but it's by no means the only source of this kind of thing. There's all kinds of, you can get apps for your iPhone that will tell you all this stuff. I swear, it's everywhere. So in this particular case, I was looking at my house in Littleton. So I look at this and it says, oh, there's the moon's out and there's clouds. So this is really not too good. Thursday and Friday and Saturday, I would probably shoot narrowband because the moon is out. It's nearly full. Narrowband allows me to have some latitude in shooting images even when the moon's out, although it's not very good. I mean, you want to try to avoid this, but I mean, if you just want to play with your scope and have some fun, you can still get some useful imagery out of this. Then down here gives you sort of a subjective evaluation of what these various parameters are: clouds, very bad. So 90% clouds on Monday, the 14th at 6 p.m. Seeing was excellent, but it doesn't matter because clouds are bad. Wind is excellent, 6 miles per hour, but doesn't matter because clouds are bad. Humidity is good, 33%, dew point 19. So this tells you there's a big spread, so you probably wouldn't have to turn on your dew heaters. And then you can look at this graph and sort of get a visual. Black is good, red is bad. And so this is what you want to look at when you're trying to figure out what you're looking at for likelihood of success. You can find this website here. They have other tools there. They will host your images. So if you like Astroben, it's like Astroben. You can post your images there. See what other people did. See what other people got in the way of imagery. What exposure times and filters did they use? And you can also get an idea of when you want to start. So this little graph right here says sunsets at 5:36. But astronomical night doesn't start till 7:07. So I wouldn't even think about starting this imaging session till 7. And then over here on sunrise, I wouldn't go any further than 5:25 a.m. So that's what all of this is useful for. So here's the link. And so it's pretty useful. So time of year, the same general process we just talked about works year round. However, for Okie-Tex, some things are, and Rocky Mountain Star Stare, you need to plan ahead. Some things are great for those times of year, some aren't. So what does that mean? If you're camping, for tent campers, winter may be problematic. I've been out in the cold at Echo Lake in February, and let me tell you, it is not a fun experience. And if you're doing this for fun, you need to be devoted. So you may want to think about how you would solve the problem of heating and operating your scope in a situation like that. I would suggest sites like Jackson Lake State Park because they have electricity, the DAS DSS because they have electricity. You can operate a heater in a small enclosed space. You can be right next to your scope, so you don't have to be cold. The other thing that's nice is there's people around you. The roads are good. You can get to a nearby hotel, communications, gas, and emergency services for that kind of thing. So be careful if you're going to go out in the wintertime, especially in Colorado. Most subjects are seasonal, so you can look at Orion's Nebula Optimal now. Obviously, everyone can see Orion. The galaxy season runs from early March to mid-May. And the other thing is look at Sue French's book, Deep Sky Wonders, for more timely details. And all this astronomy magazines are useful. Okay, so here I mentioned Echo Lake. I went up there twice, once in February, once in March for, I think it was March. I don't know, maybe it was. Anyway, I went up there twice for an outreach. And so we were with Colorado Parks and Wildlife, or I was up there, and I set up my little astrophotography rig that I'm going to show you in a minute. And it's real small. It's easy to set up, and believe you me, that's what you want when you're freezing to death, because you don't want to spend a lot of time setting something up with lots of complications. You want something simple. So if you look down here, that's a little sled. They felt sorry for me, so they gave me a little sled to haul all my gear out to this place. And then I had to dig in the ice to find solid ground to set up the mount on, because if you put the mount on there, the snow will melt underneath the foot pads, and then you don't get it. Your level will move around. So that was another thing. The other thing is I picked a bench over here to sit next to, so I could sit there with my hot chocolate. And when nobody was talking to me about what is this, what is that, that's a nice place to sit. They had a ranger out there, CPW ranger, and she felt sorry for me. She kept bringing me hot stuff to eat because there's no campfire. It was just freezing cold. With this particular rig, I grabbed this image. This is the Veil Nebula. I grabbed it on 21 September. This was with an Optolong L Extreme and the ZWO ASI 2600 MC Pro. In fact, this camera right here. So there's a camera. This is an Skywatcher EQ6R Pro mount. This is an Ioptron Tri-Pier. This is a Sharpstar 61 EDPH. This is an ASI Air controller. and the ZWO guide camera. I don't remember. I think it's an ASI 290, and then the little tiny guide scope. And so we'll go over this all in a minute. So the mount. So remember, we're talking about gear now. The mount is the most important part of your astrophotography rig. If it doesn't work, it doesn't matter how much you spend on anything else, because your images just won't work. So in the prior image, notice the two green bands. So there's a green band here. This is called, it's around this axis, which is called right ascension. And this green band is declination that goes through this. I assume you guys can see my mouse moving. Anyway, that's what the right ascension and declination. So I'm going to spend a little time telling you about what this is. So this is called a German equatorial mount. And if you see this tripod down here and you see this German equatorial mount, notice that this center part right here is the rotational axis. This axis must be pointed at celestial north, because all the stars in the sky rotate counterclockwise around celestial north from where we are here. And so because they rotate, you want a scope that will rotate with them. And so this axis is called right ascension. And so what it's doing is it's tracing a circle across the sky. Everything in the sky is going to trace a circle. I'm sure you guys have seen pictures of the night sky with long exposure. So this you want a mount that will track this, an object that traces a circle around, say, Polaris, which is close to, but not the same as celestial north. So this axis must be pointed at celestial north. The process of getting the right ascension axis pointed at celestial north is called polar alignment. So that's a very critical thing you do before you do anything else with the mount, is get it polar aligned when you're in the field. Now notice that this axis, this gimbal right here, is tracing out a circle across the sky. The circle is called, it's because of where objects are over the course of an evening. It's due to the rotation of the Earth over a 24-hour period. So the coordinates for the right ascension are not degrees, minutes, seconds, they're in hours, minutes, seconds, because it is it's important to know the time of night when you're looking at something. So if you want to know more about why it's called right ascension, what the hours and minutes, seconds mean, I recommend this second link here that this Cornell talks about what is RA and what is declination and so forth. So what this axis does is you're picking out a time for an object in the sky. You're tracing out a circle. Because every object in the sky traces a circle, you also want to know which circle to pick. That is what the declination axis does. It allows you to pick a circle, and it works whether you're pointed at north or south or anything else. So the declination is in degrees, minutes, seconds. And so the right ascension is time dependent. The declination axis is angular dependent. So this is what you want. So in the above animation, the center of the axis rotation axis must be pointed in the celestial pole. As the Earth spins around the pole and the scope is tracking to match the rotational rate, objects in the scope's field of view will appear stationary. This is what you want for astrophotography. So imagine a football-shaped object like a galaxy or something like that, something that isn't round. If you try to take pictures with a scope that has an azimuth and elevation axis, you would, over the course of a night, if you're imaging that one subject over the course of a night, the football would tend to spin. It's called field rotation, and you wouldn't be able to. You could do it; it would work, maybe, but it's a pain. So this allows the object to look the same, have the same orientation with respect to your image sensor over the course of a night. So this is why you want a German equatorial mount. Or some other type of mount that can accomplish this feat. The German equatorial mount, I must confess, is the one I have the most experience with. There may be others. I think people use Azel mounts with a wedge with Dobsonian scopes and can get the same result. So as far as remember, I'm a newbie, so be careful that there may be other approaches. I guess that's what I'm trying to say. So what does all this cost? Well, suppose you wanted to build exactly the same mount that I had. And remember, I had time to accumulate so that there's sticker shock. So you need a guide scope, $100. You need a guide camera, $300. You need a controller. This is basically a little microcontroller that's at the telescope that manages your imaging session. And this can be replaced with a computer via USB hub. But if you wanted to go with this Cadillac approach, that's $250 for, say, an ASI Air Pro. A red dot finder. If you go into outreaches and you're surrounded by kids in front of Chamberlain Observatory and they want to look at the moon, they're not going to wait for you to polar align. They want to see the moon now. So you want a red dot finder. It doesn't cost much. It's $70. So you can use the red dot finder to set up the scope to look at the moon, and you can forego all that other alignment stuff we just talked about. The main scope is obviously speaks for itself. $700 for this Sharp Star. Focal reducer. What this does, it's just some optics that sticks on the back of the scope that reduces the focal length, lowers the f-stop, makes it faster. The magnification is good, but you may want this. Oops, sorry. And that's $200. Filter wheel. So if you're taking color images, probably the best images you'll see is with a black and white camera, and you rotate some filters in front of it. Those of you old enough to remember when we were kids, we used to have these aluminum silvered Christmas trees, and we had these filter wheels that would do red, green, blue, and colors, and this tree would turn colors. It's the same thing here. So you have a little carousel that has a luminous filter, red, green, and blue. If you're shooting narrowband, probably you're going to use these three filters: hydrogen alpha, oxygen 3s, and sulfur. And those are probably going to be your most important narrowband and broadband images right here. So the ZWO 7-position filter wheel is a carousel. It'll rotate these filters so you take so many images with luminous, so many images with red, green, and blue, and so on. That's $400. And then filters, you don't want to scrimp on these, because these, a lot of times you want to get something that's repeatable, and you want to have really good calibrated filters for your results. And so you can, when you look at your results and you compare them with what other people did, and they have something that looks different than yours, at least this won't be a variable in your assessment. So a full set would be about $1,000. The Imager dedicated astro camera, but you can also get by with a 35mm camera. Many do, and get excellent results. I used a ZWO ASI 2600 mm Pro. That's a monochrome camera, but I also have the MC Pro if I'm in a hurry, or I just don't have my filter wheel installed, and I just use a single filter like an L Pro or L Extreme dual band filter. $2,500 for that camera. Electronic focuser. So I polar align the scope, and then I check focus on everything on especially my guide camera, and then I go inside. Now, I'm not going to sit outside and freeze all night. So when I go inside, I don't have to go outside and focus. So an electronic focuser is worth its weight in gold. You want to focus as the temperature changes. The temperature changing can really affect your images. $250 for that. The mount, we already talked, that's the most important piece. Don't scrimp on that. EQ6R Pro is a good selection. It just works. It's simple. A lot of people use it. It's reliable. I'll say that. $2,600. Memory stick, not much. I didn't show you. If you're in the field, you want at least a 500 watt hour battery. I use a Jackery and 100 watt solar array to charge it if you're in the field. If you go to star parties, a lot of times they'll give you some juice, and you won't need the solar array. $800 for that. Telescope cover, Astro Gizmos, $55. So with this rig, the weight capacity of the mount is 44 pounds with the EQ6R Pro. This whole rig weighed 12 pounds. So what does that mean? That means I can actually go a little bit larger, or a lot larger, with the telescope. I can upgrade the scope and not have to buy a new mount. So how big can I be? Well, the rule of thumb is, and you will find all kinds of opinions about this online, the weight capacity of the mount is 44 pounds. You don't want to go over, say, 22 pounds, half the capacity of the mount. So I could go as high as 22 pounds and I wouldn't worry. Some people say you can go as high as 2/3 of 44 or more. And I actually push the limit on me. And I can on this mount with a stellar view scope. And the problem with that is it'll probably work great, and it has worked great. But when it gets really windy and you have a heavy payload, the mount is having to work harder. So try to oversize your mount as much as you can. Also make sure these things are not light. So if you're having to carry this in the field, be sure that it's something you can carry. So we talked about this rig, which was $9,240. That's a lot of money. But I can cut it down by almost half by adjusting a few things. The controller, I went to a Raspberry Pi, I saved $50. I don't recommend doing this, but you could. A filter drawer instead of a filter wheel carousel, get rid of that. That saves a lot of money. So this only costs about $80. If you're going to use a color camera, you don't need LRGB filters, and you can just get by with an L Extreme dual band filter and an L Pro filter. And I've taken images with no filters at all and been perfectly happy. 510, so that saved you $500 right there. Imager, you can use your Canon EOS camera or your Nikon, and you need a T-ring adapter and something to get the back focus right, which I'll show you in a little bit about what that means. You can do manual focus. You don't really need this. You can save another $250. Mount, you can get a smaller Skywatcher mount. This will save you more, about $1,100–1,200. And then get rid of the memory stick. If you have enough memory on your little computer that you're going to use to control it, that saves you a little money. And so that brings the price down to $5,600. But now your weight capacity of the mount is $22. So you saved $5,000, but now you can't really upgrade this rig. You're stuck with this rig and this configuration. So you have to be forward thinking and decide, what are you going to want to do long term? That's why you want to start with binoculars and a lawn chair, because you want to decide if this really is for you and really how good do you think you'll be with it. So given that rig, that $9,000 rig, here's an image of the Andromeda Galaxy I took in my backyard in Ken Carroll behind the hogback. This was multiple exposures. I forget how many. It was an LRGB, light luminance, red, green, and blue, and hydrogen alpha, processed in PixInsight over the course of a couple of nights. And this is a single image. In other words, it's not a mosaic. I used that super wide field camera and got this image from my backyard. And it's just amazing when you see things like this, that a small rig can take pictures better than the things that 20 years ago were almost impossible. It's just fascinating. And so I think this is M101, or what is this? I forget that one, M102. I forget. There's
110.
110.
110.
Copy that, 110. And then up here, you can barely make out, there's a star cluster in Andromeda up here. That's actually a star cluster in another galaxy. Is kind of an amazing thing. So when I process this image, I don't like to see, when I add hydrogen alpha to an image, what you see is a lot of guys put in all these bright red dots just to show off the fact that they had hydrogen alpha spectra in their image. I don't like that. I like it to be a little bit more subtle. So you can see the sort of pinkish regions here. That was the hydrogen alpha contribution to this image. And I'd like to thank Dr. Roger Clark for helping me with the color calibration of this image. It's color calibration is a lot harder than I thought it would be. Dr. Clark is a member of DAS, and if you ever hear from him, you should listen to what he says. Okay, and then even cheaper, suppose you're a binocular guy and you're really not sure, you still want to take baby steps. This is probably the system for you. This is an Ioptron Sky Guider Pro mount. It's about $500, and you can take your DSLR camera, and this will give you an equatorial mount for not much money. Now, it does guiding. We haven't talked about guiding yet, but one of the things you want is to be able to track stars to precision. So there's this thing called a guide scope and a program called PhD2, which is used to keep your image in your camera precisely pointed. But if you're doing something like this, where you have a really wide field, you're taking 1 or 2 snapshots with a camera, long exposures, this may be okay for you. And it's good for backpacking. It doesn't weigh very much. I think the mount weighs 10 pounds and can manage up to an 11-pound payload, which means the camera can weigh up to 11 pounds. So you could probably put it in a backpack, but don't forget you have a counterweight here that you'll be carrying. So, and a tripod. So this is probably good for in the field, walking around, tent camping, that kind of thing. Or if you just want to learn. If you decide to take this route, and I didn't, but I did look at some of the tutorials online. The best I've seen of this fellow, Peter Zelinka, if you go to online on YouTube, he's a very down-to-earth guy, and he will give you some pointers on how to make all this work. And by the way, this isn't the only one. Skywatcher makes one. I think this is the one he favors, the Ioptron Sky Guider Pro. Okay, so there's some math behind selecting the main scope, and you're going to need a guide scope. So the guide scope, what the guide scope does is it takes a picture of a wide field, a wider star field than your main scope generally, and it keeps the target centered. So when you're taking exposures over 2 to 5 minutes, you need your mount to track the target very accurately. Usually, I think the bellwether is on the order of 1 arc second RMS, something like that. So what you need to do that is a program called PhD2, which will look at a star and keep that star centered. And its job is to send error control signals to your mount, your equatorial mount, to keep in right ascension and declination, and it will keep that star centered. Now, lately, PhD2 has added the ability to track multiple stars. Now, why is that a good thing? In a case where the seeing is bad, in other words, the star starts to fluctuate in amplitude, or you have a situation where the stars are not stable for whatever reason. You want to take the geometric mean of where where the program thinks the peak of each star is. And so having multiple stars guiding is a real neat addition. They've actually accomplished that in this PhD program. And I've seen a marked improvement in guiding. But anyway, so you have a guide scope and you have a main scope. And so let's just step through these items real quick. The focal length of my sharp star is 335 millimeters, so it's very small. The aperture is 61 millimeters. I had a reducer in there, and what this reducer does is it reduces the focal length of the scope by a factor of 0.8. So 335 becomes 268. So if you do the math, you come up with an f-stop of 4.4. Well, what does that mean? It means that the scope is fairly fast. Celestrons are, so for example, Celestron SCTs are f10, so it takes them a lot longer to take an image than this scope here is very fast. So, and then the hyperstars on the Celestrons are like f2, so a 1 minute exposure, you can get a lot of data, but unfortunately, you're giving up some magnification. This camera, this just tells you the pixel camera I was using, and then the pixels, and then the micron, how many microns each pixel is. And then I'm binning. So if you join the AP SIG, the Astrophoto SIG, we'll talk about binning and what it means. But for now, let's just go with binning 1. What it means is so if I have 1 pixel, my unit of measure of light amplitude is 1 pixel, right? I'm using 1 pixel to measure a certain section of space, a number of arc seconds. And in this case, with the optics I have, that 1 pixel is giving me 2.89 arc seconds per pixel. So this is called the image scale, and it's a critical number that you need to know for the optics that you're using. There's another number that you need to know. It's called the Dawes limit. And this guy, William Rudder Dawes, in 1867, determined the practical limit for resolving power of a telescope. It's the closest that 2 stars could be together in the sky and still would be seen as 2 stars. So this number 1.9 is the limitation of your optics. You want your image scale with your camera and all your optics to be bigger than this number. So 2.89 is bigger than 1.9, so we're okay. If it's less than, it doesn't mean you can't take a picture. It just means you're kind of spinning your wheels because this is the limitation of the physical limitation of the scope. So what could you do if it was less than? What you could do is you could increase the binning. And so what you're doing is you're taking a binning of 1 means 1 pixel. This is your image scale. If you change your binning to 2, then what happens is you're taking 2 pixels in width and 2 pixels in height. So you're taking 4 pixels and you're calling that a single pixel. The reason I didn't want to talk about this until the AP SIG is because some cameras have hardware binning and some have software binning, and there's a bunch of information to know that we just don't have time for tonight. So the DAWS limit, so we're okay here. And so the image size and width, so we have 2.89 arc seconds per pixel. So that means with this many pixels, the height and the width, my image is going to be 301 arc minutes by 201 arc minutes. So this is where Sky Safari, this is where what they use to draw the rectangle that they do of your field of view. Now, this is your imager. On the right here is basically the same, is exactly the same kind of calculation, but you have a different scope, different aperture, different focal length, different camera. And so its image scale is 4.98. What you want as a rule of thumb is you don't want this number to be more than 2 times this number, because if you start to see drift in your tracking, your guiding, a little bit here amounts to a lot on your main scope. So there's a book I have, I'll dig it up when we talk the image SIG about what actually is going on here. But the rule of thumb is this number divided by this number should be less than 2. The guider to imager ratio in this case is 4.98 divided by 2.89. It's 1.7. So we're okay. And I have results that I'll show you that basically show that's okay. Sorry. So this, if you get this slideshow, this is an active spreadsheet in PowerPoint. You can double click on it. You can see what all the relations are. But if you want to do some homework, see Charles Bracken, and we'll give you the basic relationships I used to develop the spreadsheet. There's all kinds of spreadsheets for astrophotography. This is a very simple one, and I use it all the time. Now, another thing, this is kind of a droll subject. It's called back focus. So when you buy a telescope, there's a datum line at the back end of the telescope that goes from the back end of the telescope to where the image sensor needs to be. So what you want to try to do is get this nailed. Doesn't mean if you're a little bit off, you can still focus the scope in and get it to work, but you want to try to get this nailed. So it's frustrating. It's like a little game you play with the numbers to make sure everything will add up to the right back focus. So let's take a couple of case studies. So I have a stellar view camera, and it has a reducer on the back, and the datum line is the back of that reducer. So for the data sheet from stellar view, I need to have my image sensor exactly 55 millimeters from the back of the telescope, or desired to get as close to this as I possibly can. So I have a tilt adapter on well, I haven't talked about off-axis guiders, but I have an element in the optical chain that's 5 millimeters. So that's using up some optical path. So now I take 55, subtract 5, I get 50. Now I have to make up 50 millimeters. Then I have an off-axis guider. We haven't talked about that. It has an optical path of 17.5. Take 17.5, subtract from 50, you get 32.5. And then I have that carousel, that electronic filter wheel for 2-inch filters. That chews up 20 millimeters of optical path. So that leaves me with 32 minus 20 is 12.5. And then I have my camera, which has from the front of the camera to the actual image sensor is another 12.5 millimeters. So 0. So I nailed this. So I'm using up exactly 55 millimeters, so we're good. And here's the conditions under which this is true. Then let's say I have a Celestron SCT, and this is typical. The reducer back focus from the back of the reducer to the datum line is 146 millimeters. So I have to burn up 146 millimeters to get to my image sensor. So I buy the Celestron T adapter. That's 91. That leaves me with 55, this magic number 55 again. Then I know what the rest of them need to be because I already did this exercise up here. So I can make up 55 and I can get to 0 and I'm good. So that's back focus. If you join the AP SIG and you get into a situation you're can't figure it out, this is something that is tedious, but you have to know. Okay, so we haven't talked about IT, basically your computer and your networking and all this stuff. I spent a lot of time on this. I made a lot of mistakes, and it's just the kind of thing you have to learn as you go. But maybe with this presentation, I can save you some trouble. So I started out in the field, sitting out by my telescope at night, with a USB 3.0 hub, connecting all my cameras and focusers and filter wheels and all the stuff. And I connected it to a laptop and it worked. It was great. Then I wanted to go inside because I was cold. So I used a USB 3.0 with an active repeater. Mixed results. And I was using Sequence Generator Pro as the software at the time on a laptop. And I wasn't happy with that result. So I regard this as not really reliable for what I was trying to do with keeping the laptop inside the house. So I put an Intel Nuke PC. If you're not familiar with these, they're little tiny PCs that Intel sold and still sells. And I Velcroed it to the side of my mount and I ran Windows on it. And I used Windows Remote Desktop on a laptop. And I connected an Ethernet cable or Wi-Fi and Sequence Generator Pro on the Intel Nuke and Remote Desktop on my laptop. It was great. It worked. The problem was it uses a lot of juice. So if you're in the field and that Nuke PC is going to chew up your battery really quick, or at least that was my experience. So then I switched. Yeah.
Joe, sorry to interrupt, but maybe some of the details you can leave to the AP-SIG meeting on April 14.
Okay, I'll do that. Okay. So
Thank
you. The bottom line is the two items of red are what I would recommend to you. If you like only ZWO cameras, you can use a ZWO ASI Air Pro. It's a Raspberry Pi. It doesn't use much juice. It has a dirt simple UI and it's pretty good. The other one is you can use a mini PC if you want to use stick with PCs. Using Nina, this is where I'm actually at now. This gives you more latitude on the hardware you're using. Okay, I see what time it is. Okay, sorry. So here's the electrical layout. This will show you the way you can connect it all. So I have Ethernet going back to travel router. So why Ethernet? When you go to star parties around the field or at a campsite, a lot of times people around you will have Wi-Fi that produce radio frequency interference, and your Wi-Fi will be unreliable because everybody's using the same bands. So I use an Ethernet cable going to my travel router. I have an iPhone tethered to the travel router that gives me internet. You don't have to have internet. Most of these you can run without internet at all. And then I have a little 500 watt hour Jackery. If you go the mini PC approach, it's virtually the same configuration, not much different, some slight changes. And then there's some camp specific things. So you want to use your own power for star parties and such. So 500 watt hours is the minimum I would go with. You can get a good canvas tent, cot, sleeping bag, propane stove. If you're in the field, be careful with propane heaters. They smell, they give off carbon monoxide. And believe it or not, they precipitate moisture in your tent. So you'll be warm for a while, but you'll be cold when you're wet. So probably a better choice would be a propane furnace, which is a heat exchanger approach and doesn't burn propane inside your tent. Add a bike rack. There's various reasons for that. Bring a scope cover. Traveling with a group can help. So in my latest trip with Steve Barr, a friend of mine, he had an extra USB cable that I had forgotten. He saved my entire weekend. I was out there in the field and 2 hours from home, and he had the extra cable that I'd forgotten. Or if two guys get auto guiding trouble at the same time, you can see where that would be an advantage. Finally, let's talk about two more things, and then we'll wrap it up. Operations. Here's my Okitex rig. This is a stellar view 130 millimeter APO triplet refractor. I had my flattener here, a filter wheel, ASI 2600 mm Pro, ASI Air, the same EQ6R Pro, and I got this shot of IC 342, which is kind of hard to do. So Okitex is a great place. These guys are perfect. So when you're in operations, these are the terms you need to learn for astrophotography. And over here is our links that explain what these are. Because we're pressed for time, I won't go into all of them. This is where it starts to get deep. I will tell you that. If you can get past the hardware part, this is where you start to get deep into the actual imaging and techniques. This is where you sort of need to spend some time. Okay, what is the overview for setting up in the field? This is your operational game plan. When you get up, you start from the bottom and work your way up. Set up the tripod first, then the mount and the scope, then your IT, and then you test it all. At dusk, you do your polar alignment, you focus, you take your test exposures, you want to make sure your cameras are working, and you start in what's called an auto sequence. This is your script that's going to run in your software that will automate the entire process. You definitely want to know how to do this because you will make mistakes if you try to do it all manually. It's a very tedious process, and try to make sure that you do this all automatically. At astronomical night, just before this, you just press go, basically, and it will slew to your target. It will calibrate your guiding and begin guiding on a target. It will slew to the target using plate solving, which means it'll take a picture. And if your target isn't matched to where it thinks it should be pointing, the program will automatically fix that and slew to the target and put it dead in the crosshairs. This is an amazing thing. You don't have to sit there and sync your scope and do all these things and 3-star alignment. All that's gone. The program will take care of that for you. Then it will start to take your light frames. Light frames are your frames that you're taking pictures of. This is your main objective here. This is where you're taking pictures of your target. It will autofocus. It will use star diameter as a metric. And it will do it for each optical filter because different colors, even though you're using a triplet refractor, will still have different focus points. So you use autofocus and you change as temperature changes and also as you change your filter. You want at least 30 exposures at whatever exposure time for each filter and why. Dither, we'll talk about dither in the AP seg. Dust cap, cover scope. When you're done with your light frames, while it's still dark, you want to put, even with a covered scope, you still want to do this in the dark. Take your dark frames and your bias frames and your flat frames and your flat darks if you need it. Now, I'm pressed for time, so I can't go into this. You don't, depending on your camera, you may not need all of these. In fact, you probably don't need all of these. You need to look at, there's a guy by the name of Adam Block that teaches astro image processing that talks about cameras and what cameras need which one of these calibration frames. Charles Bracken may also have some more information about that. Then when you're done, you tear everything down. You start from the top and work your way back down. So I want to go this. This is my checklist for arrival. This is setting up the tripod, mount, scope, balancing everything, adjusting my counterweights. That's all this is. And it's just a checklist. You can go through this on your own. One thing, even though this may seem kind of silly, when you've been driving for a couple hundred miles, screws and fittings are going to back out. The things that you have for holding everything together are going to get loose. So you want to shake your rig, literally, and you look for things that are loose. And believe it or not, this has saved me a couple of times. You set up your electrical, you connect everything, you turn it on, you check your current on your power supply, you make sure it's not consuming too much power, which may indicate a failure. Verify connectivity, that you can talk to all your elements. Make sure you can get images from the camera and the guide scope, the guide camera. Set your dew heater and camera image sensor. Set this as cold as you can, image sensor, because you'll get better images that way. verify you can slew your mount, restore to the home position, shut down power, everything, cover scope. So this is before astronomical night. And then you want to set up your, if you haven't already, you want to set up your script. So this slide just says, here's the kind of things you set up in your script. Different programs have different script setups. So what you're doing here is you're authoring a software script for your imaging session. The script will automate the entire process. So if you do this right, and believe me, it takes some practice, it takes some fiddling. This is one of the things you want to do at home before you go out in the field, and make sure it's right and will work. You may still have some fiddling to do in the field for different latitudes and longitudes, elevations, all that sort of thing. But you want all of this to, basically want to understand all of this. And so you try it at home. Then when you're at dusk and you remove cover and dust caps, you inspect your lenses and you do some normal stuff that you would expect. You do your autofocus, you do an initial autofocus. It's better to have everything focused before you go back in your tent or camper. You command polar alignment. You capture an image. You make sure that you can polar align the scope. So the polar alignment method I use, I don't use. I use basically an image plate solving polar alignment. So I take an image, I plate solve it, and that tells me the latitude of the right ascension and declination of the image, of the targets in the image. And then I rotate the 60 degrees in right ascension or 90 degrees, and I capture and I plate solve again. So because I have a circular arc, because my right ascension is circular, I've defined a circle or part of a circle, and that circle has a center. That center has to be celestial north. It won't be. So what this program will do is tell you how to move in right ascension and or azimuth and elevation, believe it or not, so that your center of that circle is, and it will continuously update the plate solving, and it makes it very simple. So you can use your main scope if it's wide enough, or you can use your guide scope if the main scope isn't wide enough field of view. And that's how I do it. Calibrate, focus your auto guider. We'll talk about it in the AP SIG. Mount them out to the home position, and then you execute your imaging sequence. So a lot of this, there's a ton of details in here. If you join the AP SIG, we'll go through them in detail, and we can share experiences and so forth. What can go wrong? All kinds of stuff. I mean, it's just an infinite list. But check your results at the end of the run. If you got it, images or you didn't get images, here's the kinds of things that I've seen that happen. You had degraded seeing. That means your stars were fluttery. Maybe you had clouds. The clouds went, the guide stars were lost, and so you had bad guiding. Believe it or not, cable drags and snags are a big deal. So cable management is you want to make sure that as you rotate in right ascension, you want to, before you start imaging, you want to rotate in right ascension and declination, and make sure that there's no cables causing an impediment to the free rotation in either axis. If it snags on something, my best, if you have a mount like the EQ6R Pro, go to Micro Center over in Denver and pick up some cable covers or something to make the cables clean and free of snags. The other thing you can do is you want your cables to go up along the axis of rotation. So if you have a cable that's going from the right ascension axis to the declination axis, you want the cable to transition from directly up that post that forms the declination axis, and that will save you some trouble. We'll go over that in the AP SIG. Another thing is misconfigured meridian flip. We didn't even touch on meridian flips. That's a big deal. It took me a while to figure out how to get that right. Wind. I've had images with exactly the same setup and exactly the same configuration at exactly the same place, one day apart, where the images on one night were perfect and the images on the next night, because of wind, were blurry. So wind is a big deal. And it's even more so if you're overloading your mount like I was doing. Asymmetrical vignetting. So if you If you didn't calibrate your filter wheel and you've got two filters, or say, for example, in the extreme case on the image sensor, that will cause some asymmetrical vignetting. Overexposed, underexposed, that's obvious. Camera sensor can't reach target temperature, cooler shuts down. So the ZWO cameras used to, I don't know that anymore, but if they couldn't reach the temperature, they would reset, and you'd be left with images shot at too hot, where the camera was too hot. Dew fog, you forgot to turn the heater on, dew heaters, all sorts of things. So let's skip past that. So image processing, this is what wipes a lot of people out. This is a picture of the North American Pelican Nebula taken with that little AP rig I showed you, using an Optolong L Extreme filter processed in PixInsight. Choices. So if you want to decide what image processing software you want to use, here's a website that gives you a trade study. I decided on PixInsight early on, and I tried augmenting it with Photoshop, but mostly I just use PixInsight, so that's what I'll talk about here. Learning PixInsight. I tried a book by Warren Keller. It's a good book, but it just doesn't go deep enough. And the subject matter is just too big, and it's always changing. So by the time the book is printed, everything's changed, some new features added. So online web-based training is the best. This guy, Anna Block, tries his level best to stay up to date. I really respect his training. It's long, it's wordy. He has a lot to say, but a little patience here you'll learn a lot. There's a guy in our group named Roger Clark. I really like his website. It's clarkvision.com. And I checked out, I use this, I've been looking at this for color calibration. Roger's actually commented on some of my images. It's been very helpful.
Bill, we are going to have these charts available for everyone, so maybe you can go faster on the
okay.
details.
So here's just a workflow. This is an abridged workflow. There's just some stuff you can try. The only thing I want to mention about this is when I process images, after I get my masters, I have a luminance master, red, green, and blue master, for example. I separate out the luminance master. I sharpen it. I perform deconvolution on it. I do stuff on it that I don't do to my color masters. The luminance master decides where the light is. The color masters decide what color that light is. So the luminance masters, if you think of it as going a variable from 0 to 1, if it's 0 at a particular pixel, it doesn't matter what the color is at that pixel. You're multiplying it by 0. So think of it that way. The luminance decides where the light goes. So color masters, I do a different process for that. And then finally, I combine them all in LRGB combination. I just do some denoise, color saturation, some processing. You'll get all that in the Atom Block stuff if you do the Atom Block training. That would be my recommendation. And preparing for web publication, here's, you can do this. And then save it as a high quality JPEG file. And that's about all I could fit into 4 slides. My last suggestion to you is as you're learning this, keep all your processes on 3x5 cards like recipes. I have 1 card per project, sometimes 1 card per method, depending on how complicated it is. So assessing your results. So here's the Leo triplet. I thought this was okay. So I didn't really have any comment on this. So there's some things you look at. So I'll just comment on, so there's IC410 Tadpole Nebula. This was underexposed. The color saturation is too high. I was playing around with the Hubble palette. I'm not really happy with this. I probably should have spent more time getting this image. If I had used the L Extreme, Optolong L Extreme, it probably would have looked better. I'm going to not focus on the Hubble palette as much as I used to, so it probably could have been better. Trifid Nebula. This thing was too low in the sky, and I had trees and houses in the way. This was in my backyard, and I'm completely missing this blue structure in the back. And because it was low in the sky, look how blurry the stars are. So this would have been a better one for Okie-Tex or some star party where you have crystal clear skies and everything's perfect. This is the Veil Nebula, Eastern Veil Nebula. I'm actually okay with this. This is a narrow band image. I thought it came out okay. Stars are nice and round, sharp. You can see some texture in the nebula. This was taken with a stellar view, 102 millimeter refractor. This is the California Nebula. I think a lady from the last one called it the hot Cheeto. She had a section, I think, right in here, the middle part with 110 millimeter refractor, I think she said. But this is with that little sharp star, so you get a little bit more of the structure. It's an enormous structure. It's very beautiful. The Flaming Star Nebula. This one was okay. This was done in hydrogen, alpha, oxygen, sulfur. The only thing I couldn't figure out is these stars here. I was using a refractor, so why are there these 4 spikes? I couldn't on some of the brighter stars. I just don't understand that because I don't have spider veins on my. I mean, the veins like you would have on a refractor, which cause refraction spikes. So that's curious. The other thing is some of these stars had halos like this one right here in the middle that you don't want. This is taken with that small refractor. Again, this is the trunk nebula, IC 1396 nebula, and this is the trunk, elephant trunk here. This is okay. There's a halo here I wasn't happy with, and one down here. There was a nebulosity around this one, and I thought it was going to have to denoise this until I noticed these dark structures here and realized that this is actually legitimate nebulosity. So that's one of the problems you face sometimes, is wondering what's real and what isn't. Part of the Virgo, M86, M84, lots of galaxies. You can see some down here in the lower right. Part of the Virgo cluster. I'm okay with this one. I was trying to get the Deerlick Nebula. This is the Deerlick group down here, and the Stevens Quintet up here. I got the exposure right, I think, for this structure and some of these, but in order to get those, I had to sacrifice overexposing some of these bright stars. As you can see, they're all bloated. So to me, this is an issue with composition. It would have been better to zoom in on some of these with a larger aperture. Triangulum Galaxy, I think that's okay. So if you like what you saw tonight, join the DAS AP SIG. It's myself, Greg, and Fogarty. Greg has already done a presentation on planetary. You can sign up by emailing this. Our first meeting is the 14th, and we're going to give more detailed presentations on various things. It'll be roundtable format. You share your experiences, we'll share ours, and show your own experiences. We'll do galleries. We'll have it won't be Nextcloud. It'll probably be something like our web server will probably be like OneDrive or something similar to that, very simple. Maybe we'll plan some star parties, some mini star parties going out as a group. The structure will be a Zoom meeting just like we're doing now. Wednesday night after the full moon. We'll have news, events, notifications, group Q&A, plan for our next meeting. There'll be an open forum, discuss problems you're having, group discussions, raise solutions, and new product reports. You will have little mini presentations, and you can show your pictures. We'll all want to see what you have. And hopefully we'll have a group for spectroscopy and a group for solar. So we're looking for individuals that have a lot of experience in those fields to be one of the team admins. That's it.
Thank you, Joe. It was a bit longer, but it was very detailed and necessary, because this whole topic is, as you pointed out, is quite a complicated and requires lots of learning curve, I guess. Are there any questions for Joe from the members? Please raise your hand, or I see several comments on the chat line saying that this is a great presentation, and they are thanking you. Joe is John Bickle has a question. I see. John, unmute and pose your question.
Joe, have you ever tried the approach of just taking a very large number of, like, 15-second shots at a high ISO? You know, I've seen some presentations by there's a guy, Nebular Photos on YouTube, where he's tried this approach. Just, the idea is you don't need a tracker. You just need a lot of shots, and then you let Deep Sky Stacker put them all together. You ever tried that?
I have not. That's very interesting.
Okay.
No, well, the concept is he's getting the light, he's, integrating a lot of light while the Earth rotates, and then puts it together, lets the soft, Deep Sky Stacker put it together. And it works a little bit, but it's not great for deep sky stuff. I'd say I've tried it for Andromeda and I've tried it for Orion, but I don't think you can go a lot smaller and get decent results.
I will look into that. So for high ISO, I guess with my camera, it would be high gain because I'm using a CMOS sensor.
Yeah.
So, yeah, I haven't. I have to admit, I haven't done that. I would
Okay,
expect you'd see some compression of
No,
dynamic range.
Dina has a question.
Go ahead.
Unmute, Dina.
Okay, can you hear me now?
Yep.
Yes.
What I wanted to bring up is that on the main landing page for the DAS, we're supposed to have a member photo of the month. And if you want to go to the contact page and look for in big letters, member photos, you can submit your photos at memberphotos@denverastro.org. We have a board member, Bill Cast, who is going to review those and pick a new one every month. And so right now we have one of Joe Pineda's up there, but we'd love to have them being rotated. So please submit your photos. Doesn't matter how good they are. Please submit photos so we can have a constant rotation going. That's all I had. Thank you.
Thank you, Dina. Bill, you have a comment or question?
Yes, I do. Joe, on your Excel spreadsheet that shows the design math, you end up, I'm assuming that that this is specific to the telescope and sensor or camera that you were using.
Yeah.
And you end up with an image size of 301 by 201 arc minutes. If my math is correct and my assumption is correct, does this mean that your field of view of your image is about 5 by 3 2/3 degrees? Is that correct?
That's right.
Okay, well, that explains the first question I was going to ask is, how on earth did you manage to get the Veil Nebula in one frame? But it's about 3 degrees in diameter. Your Echo Lake picture is, I really love that. But yeah, I'm used to looking at it through a telescope with an O3 filter, and I can never see much more than a third of the thing. But it's nice that it gets such a wide field. Thank you.
You're welcome.
Any other questions? I see lots of comments thanking and finding it excellent presentation in the chat line. I'm just checking whether there are any questions. Everybody is appreciating it, Joe, and thanking you for an excellent presentation, it looks like. So as I was saying, we will have these charts available definitely for those who are members of the Astrophotography Special Interest Group, but we will also have all the or most of this InReach presentations in a library down the road. So you can actually access some of these charts or all these charts in that library. Well, if there are no other questions, I would like to thank Joe for an excellent and detailed presentation. And we look forward to seeing some of you or those of you interested in this area at the special interest group meeting on April 14. In the meantime, if you have not registered for that special interest group, please do send the email to the address that Joe gave on the chart. Okay, thank you very much and have a good night.